Okay, this is Mr. Sitta. I'm going to continue with quantum theory. Okay, I explained to you, I worked through the light equation, Planck's equation, uh, and Bohr's energy states for the hydrogen atom. The next guy that came along was de Broglie. All right, de Broglie is an interesting fella. He was an actual French prince. Okay, and if you're into fashion, uh, his descendants had Hermès. If you want to have some fun, find out how much a Hermès bag cost. I think you'll find handbags that cost $500,000. So he was a scion of and his name was Louis de Broglie. And I tend to think that he became a physicist, but I tend to think that his peers kind of looked down upon him because he was coming from a very rich family, and I guess they kind of saw him as a hack. And it's kind of interesting because they should make a movie on the development of quantum theory because these characters were very colorful. Louis de Broglie was not the suavest looking guy, but his equation, what he did is he said, I can find wavelength by taking Planck's number, h, and dividing it by the mass and the velocity. When he came out with this equation, he was kind of derided because people said, well, this is crazy. If you watch some of the videos, you'll see there was an argument as to classical physics, wavelength, versus looking at light as a particle, okay, or a corpuscle, they would call it. So there was a whole movement, is how do we view light? And, half the scientists got on one side, half the scientists came on the other, and along comes Louis de Broglie, who just blew everybody's minds, because he said wavelength is related to mass. So you can have particle behavior, mass, and you can have wave behavior. And that was groundbreaking. But when he first came out with it, he was rather derided. And I don't know that one of the cool scientists was Schrodinger. And he was one of the persons that said, well, the guy's an idiot. And somebody, I think it might have been Niels Bohr, stood up for de Broglie and told Schrodinger to take another look at his equation. And when Schrodinger looked at it, he goes, well, no, he's not. He goes, this is genius. So m is equal to mass. Mass has to be in kilograms, and v is your velocity. Not necessarily at the speed of light, but in meters per second. The implications of this are simply that if you're a planet, you have a wavelength, but it's going to be really small because your mass is really big. And the smaller you get, the more noticeable your wavelength is. But you could have a baseball, and a baseball have a specific wavelength. Anything, including you, moving with the velocity, is going to have a wave-like behavior. But it doesn't become noticeable until you get into the very, very small, like an electron or a photon. So that you start to notice it, the smaller it is, the more noticeable your wavelength is. So that can kind of freak you out. I don't know whether I should do this on film or not, but if you were looking at the sun and the earth going around the sun, people will tell you that the earth circles the sun. And as the earth circles the sun, they go, oh, well, the moon circles the earth. I tend to say none of that is true. If I was to focus on the earth's motion as it moved along, and the moon out here, since they're both in motion, they're not sitting still, okay? As the earth moves around, the earth exhibits gravity on the moon, So the moon gets pulled, the moon is constantly falling into the earth. But what happens is the earth moves and the moon whips right by the earth. And then the moon ends up on the other side of the earth. And then it's pulling again. The moon's pulling on the earth and the earth's pulling on the moon, and it slingshots it back and forth. Well, you can see that in the moon pulling us, you see it as a daily tide. Twice a day the tide goes up and down, and it's a wave-like function. So if you look at the moon's path around the earth, it's actually wave-like behavior. And in response to that, the earth doesn't sit still. The earth has a little wiggle. So as the moon pulls the earth goes through a slightly less pronounced wavelength behavior. And this is true of all celestial bodies. The sun is not sitting still. The sun is moving. So as the earth circles the sun, which it doesn't really circle it, they oscillate back and forth like a sine wave. It causes the sun to waggle back and forth. And then we whip. We're really whipping in an orbit like that around the sun. So it's not so much circular motion as it's wavelength. And I think I always like to use that as an example for wavelength behavior, because you see it in the planets, but I don't hear it talked about often when I watch star shows, and I always wonder why. I think they ought to talk about it a little more. Okay. Basically, Broglie's equation, you plug in 6.63 times 10 to the negative fourth, plug in your mass in kilograms, plug in your velocity, and you get the wavelength. See, I'm not really going to even do an example of that. I'm just going to say you can plug them all in. The thing about the Broglie's equation is along comes Schrodinger, and his name was Irwin. Very colorful person if you look him up on the internet. He was quite the ladies' man in the 1920s, and had a very unconventional lifestyle. So he's an interesting person to look up. You may know Schrodinger because you know about Schrodinger's cats. Schrodinger took de Broglie's work and he said, well, we're trying to find the electron, and if I want to find the electron at energy level 1, he plugged it into Schrodinger's equation, which was based on probability. And his famous experiment that you hear him talk about in psychology and even on Rick and Morty episodes was that he looked at electron like a cat. If you put the cat in the box and left it alone for a week, when you come back, you can't see it. You can't see the electron, so you don't know whether it's alive or dead. So in Schrodinger's world, this was all based on probabilities, which drove Einstein crazy. Einstein's whole explained the photoelectric effect, which started everything. One thing I might mention just briefly is the photo, and you'll see videos on the photoelectric effect, is electrons going, light going in to a very active metal like cesium would cause electrons to eject. Well, this was an on and off philosophy. You had to hit it with the right quantity. And Einstein explained, and it's photons in, electrons out. Einstein won the Nobel Prize for explaining it. Well, that pointed towards electrons having energy levels, which became the Bohr model. But Einstein and Planck were the foundation of all this quantum theory, but Einstein never believed any of it. And his statement was, God does not place dice with the universe. He didn't like the fact that Schrodinger was using probability and statistics to explain where electrons were, the makeup of the universe. Okay, at energy level 1, Schrodinger saw that your electrons, the probability would be a sphere. He called that an S orbital. And S stands for simple. That becomes our second quantum number. What type of orbital is an electron in? For every energy level, you get an S. So you have an S for 1, 2, 3. Well, that's like the Bohr model. 1, 2, 3, 4. Your S is growing, okay? But there's a different type. The second type starts it, and I might say his designation for an S was L equals 0. Okay, and that's the second quantum number. At energy level 2, Schrodinger said, you get your S, but you get 3 different types of orbitals. One lobe is here, and we're going to call this Z, Y, and X. So he called this a PY. It's a p orbital. You get 3 p orbitals. Okay, I'm going to remember what a P stands for, but I'm having a little moment here. P stands for principal. That's just trivial, simple principle. You also get a P in the Z direction. This refers to the axis it's oriented. That question is always on a test, and that drives people crazy. They always get it wrong. The letter just means which axis are you on, X, Y, or Z. And finally, there's a third P here. And one orbital holds 2 electrons. And I like to call it a domain of an electron. It's where the electron lives. So if you put those P's together, superimpose them, that's the flower. We looked at that model early on of the modern model. These are the 3 P's, and you would have an S right on top of them. Now, as you start growing at energy level 3, you get other opportunities for orbitals. In the P, there's room between the lobes. That room between the lobes becomes your next orbital, which I can't draw it. Okay, I might be able to draw 1 or 2. I can't draw all of them. The lobe is in between the 2 axes. So it's like here in 3 dimensions. So it looks like a star here, 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 and here. That's one lobe. You get 3 of those, you get 1 on top, and then you get 1 lobe that looks like a P, but then you get a circle around it. The electron could be here or here. Those 5 are D. D stands for dimensional, and there's 5 dimensionals. Okay, a P is L equals 2, a D orbital, and you're better off looking online or in the books. And I tell you the truth, I want to go nuts because I have all these pictures saved and they're just blank. If I go to my cloud folder for some reason, they can just disappear. And it disappeared into thin air without any explanation from anyone in IT as to how much stuff can just disappear. I said P is L equals 2. That's wrong. P is L equals 1. D is L equals 2. That's a 1. Start to get aggravated on tape. D stands for dimensional. Okay. I'll show you a little bit more of them, how they work and where they come into play. Okay. They actually come into the periodic table. And I made this little worksheet, which I will post, which did get deleted. Thank goodness. Okay. If you know this chart, it's like a cheat sheet for quantum. So first of all, it says what types of orbitals there are. S, P, D, F. Smart people don't forget their orbitals. S, P, D, F. That's how I can remember the orbital types. Here's where they are. In the periodic table, they occur in blocks. This block right here that's colored, that's your S. This block that's colored, that's where your P's filled. Okay, each orbital holds 2 electrons. There's only ever one s, and it holds 1 2 1 2 1 2 1 2 1 2 and 1 2. Your p's hold 1 2 3 4 5 6. 3 of them times 2 holds 6. The dimensional are d block. They start filling here. They're your transition metals. There's 10 of them if you count across. 1 2 3 4 5 6 7 8 9 10. Divide 10 by 2, you know that there's 5 d orbitals. The next block is F, which stands for fundamental. Now you know what they all stand for. There's 14 blocks across, so there's 7 F orbitals on any level. There's 3 p orbitals at any energy level going up and down, and your energy level would be 1, 2, 3, 4, 5, 6, 7. If you do this on a test, I will give you this, and it helps you understand everything. N equals 1, 2, 3, 4, 5, 6, 7. Okay, let's go back up to here. The L number designation, okay, S's are always designated as a 0, P's are a 1, D's are a 2, and F's are a 3. Okay. The energy level which they start at. S's start at level 1. So if I looked at hydrogen, it's got a 1 S and 1 electron. Helium is energy level 1. It's actually, sometimes they move it here. They'll put helium right there for blocks because it's really not in the P, it's in the S. So that'll be S2, completing your S. Okay? Where do P's start? Well, you see the 2 right there. P's start at level 2. S's start at level 1. So when I see S block, I always go L equals 1. Sorry, L equals 0. When I see P's, I go L equals 1. When I go to D's, I go L equals 2. Okay, it's another, and you might say to yourself, well, why do they call it SPDF and 0, 1, 2, 3? Well, that'll only make sense when you see the third quantum number, which you haven't seen yet. Okay, and then D's start at the, remember I said before on the other video, this is level 4, but for a D, it's level 3. So this will be 3D. 3D1, 3D2, 3, 4, 5. That would be 3D5. The last one would be 3D10. The first one would be 3D1. They each get, as you add an electron, the top number is the number of electrons. So if I go down, I got 4D5, 5D5, and 6D5. If I get to the end, 4D10, 5D10, and 6D10. A little off there. 5D10. Okay. For S's, if I fill them up 1, 2, I would get 2S, 2, 3S, 2, 4S, 2, 5S, 2, 6S, 2, and 7S, 2. The first block would be a 1, the second block would be a 2. They refer to the number of electrons in it. When it comes to P start at level 2. Oh, where did D start? Level 3. Okay. For a P block, I got level 2. I'm going to do this one right under 15. That'll be P, 3. 2P, 3P, 3. Each time we go down, level 4P, 3. Level 5P, 3. Level 6P, 3. Level 7P, 3. Something I'll mention. Mendeleev created the periodic table, knew nothing about any of this. This is the periodicity, the repeatedness of why things act similarly chemically. He noticed the periodic functions in their excuse me, in their chemical and physical behavior. Well, it had to do with the number how many electrons it had. When you get to the very end, 2p6, 3p6, 4p6, 5p6, 7p6. Noble gases are not reactive because their orbitals are full. There's nowhere to put extra electrons. It would have to put them out on the extra energy level, but there's not any protons, nuclear attraction. It's all canceled out by electrons, so there's no attraction for adding more electrons. And the other thing is they don't give them up. They don't give them up because they have maximum number of protons. That's our Z effective that we mentioned before. They have the highest Z effective. So noble gases neither gain nor lose electrons. So when we think about chemical behavior, we just kind of ignore them. They don't have a real high electronegativity, attraction for electrons. Go to the left. The first one would be 2p1, 2p2, 2p3, 2p4, I'm not seeing real good. 2p3, 2p4, I really messed this up. 4, 5, 2p6, and 2p7 at the last one. I guess you don't even want to look at that one. That was so ugly. I can go across at the 3p. Did I just say 3 for it? Yeah, 3, 4. Yeah, no wonder it. You know what? Let's just forget about that because I just totally screwed it up. Let's go over here. 2p2. Now going down. 3p2, 4p2, 5p2, 6p2, and 7p2. So all these would have been p1. Kind of got my subscript mixed up with my coefficient. It's late. I always make these tapes late. Going across, 1, 2, 3. This would be nitrogen. This would be oxygen. 2p4. And then 2p5 would be fluorine. Going across, 3d1, 3d2, 3d3, 3d4. This would be 3d5. Then 3d6, 3d7, 3d8, 3d9, and 3d10. Okay, and on any one of these, this would be 2s1, 3s1, 4s1, 5s1, 6s1, and 7s1. A little screwed up because my white line is like right in the middle. The white box kind of threw me off. Okay, so I didn't talk about F's yet. F's start at level 4. And so when you have an F, if you follow this pattern, this is a nice chart for you to know on the exam. You actually want to use this on the exam. Starts at level 4. So my first F would be 4F,